Class, welcome back. So now we want to continue. Last class we talked about de Broglie, who said that particles can have both they can have wave properties also. So this theory was further carried out by Heisenberg. Heisenberg uncertainty principle. So Heisenberg stated that the product of uncertainties in both position and speed of particle is inversely proportional to its mass. So he is saying that, so for example, we have the position which is x. The uncertainty in the position is delta x. And we have the velocity which is v. The uncertainty in the velocity is delta v. And m is the mass. So he's saying that both the position and the speed of particle is inversely proportional to its mass. So what does this mean? Let's look at what does this mean. He is trying to explain that the more accurately you know the position of a small particle, like an electron, the less you know about its speed. Because they behave like waves. Because their wave property is more than their particle property. Because they are too small. Just like a wave, we can't catch a wave. So according to classical physics, not quantum, particles move in path determined by the particle's velocity. That's classical physics. It means by the velocity in which a particle is moving, you can be able to know the position it will be at a particular time. But with small particles, because their wave property is more, it is not possible. So because we cannot know both the position and velocity of an electron, we cannot predict the path it will follow. Because it is behaving, its wave property is more than its particle property. So the best we can do to describe is the probability that an electron will be found in a particular region. And we call this orbitals. Not orbits. So that's the best description we can say about electron. The probability that we can find an electron in a particular position. That's the definition of an orbital. Quantum numbers. Calculation shows that the size, the shape, and the orientation of an orbital in space are determined by integer terms in the wave function. So this probability of finding an electron in a particular space, which we call an orbital, calculations have been done to show that their size, their shape, and their orientation can be determined by 3 integer terms in the wave function. We'll see what the wave function is. In the wave function. And these integers are called quantum numbers. We call these 3 integers quantum numbers. So the first quantum number is the principal quantum number, which is n. The second is the angular momentum quantum number, which is L. Take note, these are integers. They are numbers. 1, 2, 3, 4, 5, 6, 7. Describing the orbital of an atom. The third is the magnetic quantum number, ML. Then we are going to have a fourth, which is the spin quantum number. Principal quantum number, what does it describe about the orbital? N, which is the principal quantum number, characterizes the energy of the electron in a particular orbital. This tells us the energy of the electron in a particular orbital based on the position in which the orbital is. That is N. N can have integers from 1 and above. It cannot be 0. So N can only be 1, 2, 3, 4, etc., etc. The larger the N, the more energy the orbital has. The larger the value of N, the larger the orbital, the size increases. As N gets larger, the amount of energy between the orbitals gets smaller. So as N gets larger, the difference in energy between the orbitals gets smaller. So let's see a diagram about how N is. So N techno, it describes the energy. That's why we have energy here. The arrow shows that the energy is increasing. This is N equals to 1. This is our constant, Rydberg constant. This is N equals to 2. This is our Rydberg constant. The energy, the energy for N equals to 1. This is the energy for N equals to 2. Energy for N equals to 3. So you see the energy is getting there. But you look at the space between them. They are smaller. They're smaller. They're smaller. From N equals to 1 to N equals to 2 is very large. But from N equals to 2, N equals to 3, the difference becomes smaller. So these are principal energy level. This is how they are arranged. Let's talk about the angular momentum quantum number, L. The angular momentum quantum number determines the shape of the orbital. This is L. L can have integer values from 0 to n minus 1. Integer values from 0 to n minus 1. Each value of L is called by a particular letter that designates the shapes of the orbital. And all this is because we don't want to confuse it with the integers for the principal quantum number. So this is S orbital. This is when L equals to 0. We call it the S. When L equals to 1, we call it the P. They have different shapes. When L equals to 2, we call it the D. When L equals to 3, we call it the F. S orbitals are spherical. P orbitals are like two balloons tied at the knots. D orbitals are like four balloons tied at the knots. And F orbitals are like 8 balloons tied at the knots. You can try this at home. Get balloons, blow them in the same sizes, and tie them so that you make these orbitals. So that's what we are saying. Principal angular momentum quantum number. They have value from. They have values from. So these are the values. You have L equals to 0 is S. L equals to 1 is P. L equals to 2 is T. L equals to 3 is T. So they have values from 0 to n minus 1. So when n equals to 1, L equals to 0. When n equals to 2, L equals to 0 and 1. When n equals to 3, L equals to 0, 1, 2. Yes. So that is it. Because they have values from 0 to n minus 1. We want to look at the next quantum number. Magnetic quantum number. We are going to designate it as ML, lowercase l. The magnetic quantum number is an integer that specifies the orientation of the orbital. Orientation. Is it facing x-axis? Is it facing y-axis? Is it facing z-axis? So orientation is described by the magnetic quantum number. So the direction in space the orbital is aligned relative to the other orbitals. That's magnetic quantum number. The values are integers from minus L to plus L, including 0. So if L equals to 0, ML lowercase l equals to 0. If L equals to 1, ML equals to minus 1, 0, plus 1. If L equals to 2, ML equals to ML equals to minus 2, minus 1, 0, plus 1, plus 2. So look at that. So that is how you have, that's how you can have ML. The next quantum number, which we are going to look at, is the spin quantum number. MS, we look at MS. So the spin quantum number specifies the orientation of the spin of the electron. It can either be up or down. So electrons can either spin like this, or they can spin like this. So all the electrons have the same amount of spin. The amount of spin is the same. But it can either be up or down. Spin is quantized with only two possibilities. Spin ms plus half or ms minus half. So plus half is up spin. Plus half is up spin. Minus half is half spin. So with these four quantum numbers, no two electrons can have the same spin quantum numbers, all the four. No electron. No electron. Because each electron would have its own different spin quantum. the four quantum numbers. Each electron has its own. No two electrons have the same. So describing an orbital. Instead of N, L, and M describe one orbital. Orbitals with the same value of N are in the same principal energy level, also called principal shell. Orbitals with the same value of N and L are said to be in the same sub-energy level, also called subshells. So let's just examine energies and shells and subshells. Let's look at this. So let's look at principal energy 1, 2, 3, and look at the number of subshells they have and the number of orbitals they can have. So principal energy level 1, this is N equals to 1. It has how many subshells? Just one, the S subshell, and L is 0. And how many S orbitals is going to have? Just one, ML equals to 0. And each orbital can take only 2 electrons because it's either spin up or spin down. So if it is MS, which represent electrons, it's 2 electrons, spin up or spin down. So 2 electrons. Maximum for an orbital. Let's go to principal quantum number 2. We say it can have only 2 subshells because L will be equals to 0 and 1. So when L equals to 0, how many orbitals is it going to have? ML equals to 0 because ML is plus L, 2 minus L, and 0 is 0. So this. And how many electrons can this contain? 2 electrons. Spin up and spin down. Let's go to the p subshell in the N equals to 2. L equals to 2. Sorry, L equals to 1. So how many orbitals can it have? Minus 1, because this is minus L. 0, then plus L. So it can have a maximum of 3 orbitals. And how many electrons can it have? 6 electrons, because each orbital can take only 2 electrons. Let's go to N equals to 3. N equals to 3. How many subshells are we going to have? How many L's? We have L is from 0 to N minus 1. So we can have L equals to 0, L equals to 1, and L equals to 2. Now let's look at how many orbitals can they have. L equals to 0, of course. ML equals to 0, just 1. How many electrons? 2 electrons. Spin up, spin down. L equals to 1, it can have 3 orbitals. How many electrons? 6 electrons. Spin up, spin down in each orbital. Then L equals to 2, you see we can have 5. So 10 electrons. Spin up, spin down. In summary, summarizing energy and sub-energy levels. Energy and sub-energy levels. So the number of the number of sub-levels in any level is equal to n. Take note. The number of sub-levels in any level is equal to n, the principal quantum number. Therefore, n equals to 1 has only one sub-level. N equals to 2 has only 2 sub-levels. N equals to 3 has 3 sub-levels. N equals to 4 has 4 sub-levels. So the number of orbitals in any sub-level is equal to 2l plus 1. Therefore, the S sub-level has only L equals to 0, has one orbital, just one orbital. And the P sub-level has 2. P sub-level L equals to 1 has 3 orbitals. And the D L equals to 2 has 5 orbitals, and so on. And the number of orbitals in a level is equal to n squared. So the number of orbitals in the level is equal to n squared. Therefore, n equals to 1 level has 1 orbital, because 1 squared is 1. N equals to 2 has 2 squared, which is 4, and n equals to 3 has 9 orbitals. So that is where we will end with energy levels and sub-levels and orbitals. And we even talked about the number of electrons in each orbital, which we can use to get the number of electrons in each energy level and each sub-level. Thank you so much. We'll continue from there.